Okay, here we are for chapter 23, electric currents. We'll focus on essentially what a current is, what a voltage is, what resistance is, and that'll lead us into Ohm's law. From Ohm's law, we'll talk about direct versus alternating current, and some power transmission, and we'll end this on electrical circuits. So yeah, good amount of material. Keep in mind, follow D2L and Mastering Physics to get updated on due dates and everything. I'm recording these a bit in advance, so I don't really have due dates to give you as of now, but well, as of me recording this. But if you look on D2L, you should see something. Just let me know if you got any questions. So yeah, let's start with Ohm's law, or more specifically, current, voltage, resistance, and that'll get us to Ohm's law. So first, what is a current? A current is any flow of charged particles. So usually we discuss currents in metallic wires or copper wire, and that current is made up of electrons moving through those metallic wires. So the electrons are the charge carriers, and they're moving through an atomic lattice. So remember, a copper wire isn't an empty tube made out of copper; it's a solid copper wire, and electrons are moving through it around the atoms of this copper. So there's a lot of things in their way. Not an open tube. And so, yeah, and of course protons are bound in the nuclei. These are the atoms that the electrons are bouncing into. But you can also have a current in a fluid, meaning you can even have positive charges moving if you're through a fluid. More so if you have some sort of fluid that's saturated with some sort of charge. It could be electrons, but it could also be positive ions. And you have that fluid moving, well, now you got a current. We don't have any sort of metal or metallic wires involved, rather just free charges in a moving fluid. So which of these statements is true? Electric current is the flow of electric charge, or electric current is stored in batteries? It's just A. Electric current is a flow of electric charge. So batteries do not store current. Rather, they store energy or voltage. So the battery is more like a pump. It's not what gives us the current in our wire. If you remember, we said in chapter 22 that the wire already has electrons, right? The wire is made up, it's a solid object, it's made up of atoms, and those atoms have electrons around them, and it's the electrons in the outer shell of those atoms that we use for current. So the battery is more like a pump, right? And we'll come back to that analogy. So how do we measure current? Well, current is the flow of charge, so we measure it as the how much charge per time. So it's measured in a coulomb per second, 1 coulomb per second, and we've named that an ampere or an amp, right? So when you hear about something is 5 amps or 6 amps, that means it's 5 coulombs per second of current moving through our wire or whatever it is. One common misconception is that currents move at the speed of light. That's definitely not true. One, electrons have mass, so it's impossible for them to move at the speed of light. Can they get close to the speed of light? Yeah, definitely, but they don't. That doesn't happen in a current. So electrons in a current move at about 1 millimeter a second, so really slowly. So again, how come when I flip a switch the lights turn on immediately? Well, because there's electrons already existing throughout the wire, including the filament in, say, an incandescent bulb. So as soon as I turn on the switch, I essentially connect the battery, and I start pumping, quote unquote, these electrons, and they move at every point, right? So it's like a train. Every car of a train moves together. You can't have one car in a train move without the car in front of it or behind it moving as well. So charge flows through a circuit whereas voltage is established across a circuit. So voltage is definitely not something that flows, but something you establish across a circuit. When you have a voltage difference between two ends of a wire, you get current moving. Let's look a little further into that, right? How is it that these charges move? In other words, what is a voltage difference or potential difference? Well, and so first, remember that voltage is synonymous with electric potential. And so a potential difference or an electric potential difference or a voltage difference, those are also synonymous. Those mean a difference in electric potential or in voltage between two different ends of some wire. So think about it as in this image, right? This U-shaped tube. We have water on either side, and one side has water at a higher level than the other side. So the shallower side has a lower pressure, right? There's less water at this point, right? There's less water above this point right here than there is above this point right here. So we have a high pressure on this end, low pressure here, and what happens? That high pressure pushes the water through the U-shaped tube until it reaches equilibrium, until the water level on either side is the same. So if we want that flow of water to continue, we need some sort of pump that would keep this pressure difference, right? And so we get something like this, right? So when we have a pump installed, this pump will take water and from the low pressure end and put it into the high pressure end, and that keeps that pressure difference. And by sustaining a pressure difference, we have continuous water flow. That's basically what a battery is. So a battery or a generator, they essentially take the voltage or potential difference and keep that potential difference between two ends of a wire. So if I just hold up a metallic wire, a copper wire, there's no current through it, right? Because there's no potential difference. But as soon as I attach a battery or some generator, again our electrical pump, then we're able to keep those two ends at different potentials, and that causes current or charge to flow between those 2 points. Wherever you have a potential difference, you have an electric field. So again, you attach two ends of a wire to a battery. That puts one end of the wire at, say, 9 volts and the other end at, say, 0 volts. And current falls through that difference because an electric field has been created across that wire. And that electric field is what's propelling the electrons through the wire. So once you have applied a potential difference across some wire, positive charges in that conductor or in that wire will flow from higher potential to lower potential. So again, if I attach a 9-volt battery to some circuit or to some wire, one end is at 9 volts, the other end is put at 0 volts, and positive charges would go from the 9-volt and the higher potential end to the lower potential. But as we know, it turns out that electrons are what actually flow, not positive charges. And so electrons go from the low potential end to the high potential and end. That's probably somewhat confusing, right? And so here's the problem. Current is defined as the flow of positive charge. Because when physicists started initially, they were called electricians at the time, not the same as today's electricians. But when they originally studied electricity, we didn't really know what it was. Some people thought it was a fluid. Some people thought there were two different fluids. And so it was actually Benjamin Franklin who gave electricity its name, essentially the positive and the negative parts of it, right? Today we call them charges. He called them fluids, and he assumed, right, that he just chose one of them to be positive and chose one to be negative. There's nothing positive about positive charge or negative about negative charge, other than that they're opposite. So he defined current as moving positive charges, and this was before we really understood atoms, let alone electrons, as being charge carriers. So eventually we found out that it wasn't the positive charges that move, but the negative electrons that move. And instead of redefining current and all our equations, we decided to just to leave current as being defined as moving positive charge, although in reality it's the negative charges moving. So we'll come back to this, but when you look at a circuit diagram and you see the direction of current, in reality the electrons are moving in the opposite direction. But that really doesn't change much in terms of our mathematics. You won't have to worry about this too much, but it's good to know. All right, so how do batteries work? We're not going to go too far into this, but it's essentially they work through a chemical disintegration of zinc or lead in some sort of acid, and the energy that we're getting is the energy that's stored in those chemical bonds. So you break those bonds, and we get energy released. Some old physics books like to explain a battery essentially as an escalator for electrons. So electrons come in one end, and the quote-unquote escalator lifts them up to a higher potential so that they can fall back down. It's an interesting analogy. All right, so there's one more piece to Ohm's law. We know that current is moving charges, and we know that voltage is what allows or causes our charges to move. Is there anything that inhibits that motion? And yes, that is resistance. Anything that a current will move through will likely have some amount of resistance. It could have a low resistance, it could have a high resistance. And the resistance is anything in that circuit that inhibits or slows down some current flow. Now, wires on their own, copper wire, metallic wire on their own, have pretty low resistance. So what we have are things called resistors, right? Resistors are specific circuit elements that have measurable resistance, and we can use that to help regulate current. So the more resistance in a wire, the less current, right? And so what is the resistance in a wire? Well, it's all those atoms that are in the way, right? We have this atomic lattice, and electrons are moving through, and they're going to bounce into the atoms occasionally, or the nuclei, and they're going to bounce into each other occasionally. So that slows down the motion of these electrons. So higher density materials or resistors will have higher resistance because there's more atoms in the way. At the bottom here, you can see this symbol, the zigzag symbol. That's the symbol for a resistor in a circuit. You will see that again when we get to the circuits. So, what does the resistance of a resistor or of a wire or of anything depend on? Well, if you see the equation on the bottom, it depends on three things. It depends on the resistivity of the resistor. It depends on the length and its cross-sectional area. So the resistivity, that's related to the density, which is why we use that rho, that Greek letter rho, which is also used for density. So different materials have different resistivities that define how much resistance, electrical resistance, it has. So the higher the density, the higher the resistance, essentially. Then the higher the length, the higher the resistance, right? Imagine trying to squeeze Play-Doh through a hollow tube. The longer the tube, the harder it's going to be to do that. And then it also depends on the cross-sectional area. It's inversely related to the cross-sectional area. So the larger the cross-sectional area of this tube, the easier it is to push Play-Doh through it. Similarly, with currents, right? So the longer the wire and the thinner the wire, the harder it is to get charges through it. So that all affects the resistance of our wire. Temperature also affects resistance. The higher the temperature of the filament, the more the atoms vibrate and move around, and the more they get in the way of the electrons trying to move through. So higher temperature increases resistance. All right, now we got Ohm's law. Let's look at this in the next video.